We move now to the second presentation by Sergei Chupakny.
Thanks a lot. Yep. Good day, everyone. Thank you for having me here. My name is Chupakny Sergei, and my talk is going to be about retardation of the fatigue crack growth using residual stresses induced by the laser shock pinning. As an introduction, I want to show some slides most of you are already familiar with. Is in terms of the crack initiation and the subsequent propagation to the failure of the structure. This is the main problem, and the aircraft industry requires new cost-efficient solutions for fatigue life extension of aging aircraft fleet. In this regard, compressive residual stresses can be used in order to mitigate already existing cracks or prolong or delay initiation of the cracks. Laser shock pinning is one of the most promising techniques for generation of residual stresses. Briefly can be described as follows. So the laser forms plasma on the surface, then it leads to the propagation of the high pressure waves in the material, plastify material with the subsequent generation of residual stresses and it. So the main LSP laser shock pinning parameters are the laser energy, the optic, so the size of the spot that generated on the surface, and the amount of overlap on the surface. Many times shots will be done. So, and the challenge here is to correlate laser shock pinning parameters with the shape of degenerated residual stress profile. But before we move forward, first we need to measure it, and in my work, hole drilling technique has been used. So, specimen with the processed surface and stresses in it, first drill here, and the interferometry technique here measured strain relaxation around the hole, and then using some algorithms, the residual stresses can be calculated back as originally existed. But the problem is that this technique is based on it assumes material elasticity, and when we measure residual stresses here over depth, when we measure residual stresses not exceeding approximately 60% of the yield strain, so measurements are correct, but when we residual stresses more than, or they approach 80 or even more percent of yield stress, some plasticity occurs, leading to the stress errors in measurement. So, and the challenge here is to develop methodology for correction of those errors by using this methodology. And here, fatigue crack tests, crack propagation tests are shown on the CT50 specimen made of aluminum 2024 T3, which is widely used in aircraft applications due to mostly its high strain to weight ratio. And laser shock pinning treatment is done here, exactly at the area close to the propagation of the crack. And when the crack enters, crack is decelerated, leading to the improvement of fatigue crack growth. And the challenge here is to find the correlation between the LSP parameters and the fatigue life improvement, so that we are able to predict life using defined or given LSP parameters. So those two challenges are addressed in my work. So, and first I want to start with the development of the stress correction methodology. Here you see a 3-point bending test with the specimen in it, which is bended from the top, and the hole drilling measurement is applied from the bottom. Basically, we measure those bending stresses. It's been done, 4 tests, results are shown here. The bending stresses over the depth, you see, and the measured results and the simulation as well. And you see here when the residual stresses approach approximately 65%, or even more, 80% of yield strain, that we have overestimation in measurement, and this problem needs to be solved. And the cause is the plasticity formation around the hole. So, and using our simulation model, we can move forward by applying defined material parameters to the simulation model, and then the simulation gives us amount of error for the stress error in measurement for given stress shape of the stress profile, typical LSP laser shock pinning generated stress profile, and for given materials, simulation can give us the error that needs to be corrected. And this procedure can be repeated many times with different material parameters and different laser shock pinning residual stress shapes in order to generate more statistics. And for every single case, we can obtain an error here. So, and then artificial neural network can be applied in order to learn this complex relationship between input parameters right here, which are defined in materials and the residual stress shapes. Here they are in input parameters in dimensionless form, and the output here is the amount of error that needs to be corrected right here. And this complex relationship is learned using this artificial intelligence right here. So over this all generated statistic data, in my case it was 200 simulations, and it's the process of learning called training of neural network, and this was been done more than 500 iterations, so in this case it's called epoch. Since we have this problem solved, or neural network is trained, we can go to the solving of inverse problem. So let's assume that we have already the material with a known parameter, and then given measured residual stress profile that we have, and then we apply training neural network for solving inverse problem, and neural network gives us the correction or the stress profile that originally existed in a material. So this is the stress correction methodology. So now we are able to measure residual stresses correctly. So the second part is to do the optimization of laser shock pinning with regard to the residual stresses. So this is the typical laser shock pinning profile induced by the laser shock pinning profile. And the question is here, what are the main quantities or the stress values can be used for improvement of the material of the fatigue behavior? First of all is the sub-second stresses. So they can delay initiation of the crack. And then the maximum stresses as well as the integral stress area under the stress profile can have an influence of the propagation of the crack. So what crack already exists. And so here the challenge is to find a correlation between the laser shock pinning parameters and those free quantities that might have an influence on the fatigue crack propagation. So for this case, general full factorial design has been used. All right, so Russ? It's over here. That's right. That's right. So in this case, a general full factorial design has been applied, which allows us to capture not only parameter interaction, not parameter effects, but also the interactions. And the parameters that were optimized are energy per pulse, then the optic or the size of the spot, and the amount of overlapping, so basically the amount of shots on the surface. So tests were conducted. Here the results are shown. And you see here that those stress quantities that needs to be optimized, they are plotted right here at a certain values that from our experience and from the literature might have an influence on the fatigue crack propagation. So, and they are plotted over the laser shock pinning parameters. So to be clear, those areas, they overlap each other. So, and the areas where they overlap each other, all those frees here are called feasible regions. So basically those regions that satisfies our stress quantity values all free at the same time for fatigue life improvement. And we see here that actually the feasible region here lies at the higher energy and overlaps. And now we apply our previously developed stress correction methodology, and we see that the region is shifted even towards high energy and high amount of overlapping. So, and this is the optimization of the laser shock pinning process, and now we can move forward to the application of residual stresses for the fatigue life improvement. So, you see here, CT50 specimen made of aluminum 2024 T3, and the laser shock pinning can be applied just in front of the crack propagation. But now the question is, what are the laser shock pinning parameters should be used? And now, we assume that the integral stress area under the stress profile might have an influence on the crack propagation. What we do is following: we take two treatment values right here, which lead us to different shapes of laser shock pinning residual stress profiles but that have the same integral stress area under it. And we assume that they should lead to the same or comparable fatigue life improvement. So here are the results. You see here that the crack length plotted of the number of cycles for these two different laser shock peening treatment conditions. I see here that they are, in this picture, the quite large experimental scatter are presented. And the explanation for such high experimental scatter might lie on the high standard deviation or experimental scatter and generated residual stresses as well. And I see that both treatment conditions lead to a comparable mean value, but the standard deviation for 4.8 joule is higher. That's why I have higher scatter. But when we fit the model, in this case, two parametric viable distribution into the data, we can say that those data, those two curves, they intersect approximately 9% probability to fracture. So that means that if we use those both treatment conditions, the minimum, or in this case 9 to 10 probability of fracture, we can say that with we can doubly say that we minimum increase will be guaranteed for those treatment conditions. So, and then you see here that the crack growth rate is plotted over the crack length, and here just the road of the crack can be followed, like you see it when the crack is entered in the tensile residual stresses. Right here, the crack is accelerated even higher than the reference specimen, base material, without any treatment. And then when the crack enters the compressive region, crack decelerates here. So basically, due to the compressive residual stresses and the crack closure phenomena right here, and then the crack enters this area with the tensile residual stresses again, it's accelerated up. So this is my work, and what I want to emphasize here is that the 3 steps were complex. First, the residual stresses, stress correction methodology were developed, and then the laser shock peening was optimized with regard to the generated residual stress profiles. And now this work attempts to use residual stresses for prediction of the fatigue life. Basically, when we have given profiles, we can say that minimum fatigue life improvement will be guaranteed. Yeah, thank you very much.